Okay, let's resume this lecture about hypothesis testing errors by looking at the type 2 error that a hypothesis test can make. Continuing to look at a two-tailed test for the mean, we have the hypothesis that mu is equal to some number m against the alternative that it's not equal to that m. The test statistic, as we've discussed in the decision rule, this is all the same setup. Okay, so we specify hypotheses, calculate a test statistic, and then make a decision on that basis. Now, type 2 error is the decision that we make to not reject the null hypothesis when the null is false. What this means is, if the population mean, so if the null hypothesis is false, then the alternative hypothesis is true, which means that mu is different from m. Okay, but the t-statistic that we calculate in order to implement this decision rule turns out to fall between the critical values, or alternatively, the p-value turns out to be greater than 0.05, either way. Okay. So in this situation, if the t-statistic falls between the critical values, or if the p-value is bigger than 0.05, or bigger than alpha, then the null hypothesis would not be rejected. Okay, even though in the population, unknown to us, the statistician, the mu is different from m. So what we're interested in here is, first of all, acknowledging that this kind of error can occur, right? This is one of the possible errors that can arise when doing a hypothesis test. And also just to think about what the probability of a type 2 error might be, how we might calculate that. This is different, so we don't specify this. In the case of a type 1 error, we specify the probability of a type 1 error as being alpha, 0.05. With a type 2 error, we don't specify what that is. It just kind of happens, and so we need to try and work that out. Alright, here's how we start trying to think about how a type 2 error might arise, and in general what gives us the opportunity to reject the null hypothesis. What gives us, I guess, the information to reject the null hypothesis when the null hypothesis is false. So here is the test statistic, the t-test statistic, which is formed from, we're going to particularly focus on the top line here, the difference between x bar, our calculated sample mean, and m, the null value, the number that's of particular interest. Now we can take this test statistic that we calculate, and for theoretical purposes, not for computational purposes, we can write it like this. So what we've done here is to break up this test statistic into two parts. The difference of x bar from the underlying population mean, which in general we don't know, right? But here's x bar minus mu. And then plus mu minus m. So this is the difference between the population mean and the hypothesized value for the population mean. Now, these two expressions that we've written down here are equal because these values for mu just cancel each other out, right? We have a minus mu here, we have a plus mu there. So those two things cancel out and we'd be just left with x bar minus m. So these two bits here, when you combine them, do give us the t-statistic. We haven't changed anything, but we've just broken up the statistic into two parts, which have quite different interpretations as to how they work in the hypothesis test, what roles they play, these two parts. So, first of all, this first part is something that we would recognise because we did quite a bit of work on expressions of this form when we were talking about the central limit theorem and sampling distributions for the sample mean and this kind of stuff. So going back a couple of lectures now, we found that because of the central limit theorem, the sample mean minus the population mean, whatever that is, we don't know it, but whatever it is, sample mean minus population mean divided by the s minus square root of n, that's approximately normal with degree, not normal, t-distributed with degrees of freedom n minus 1. Okay, so because we've got the sample standard deviation down here is what gives us the t-distribution over here. So what that means is that in this representation for the t-test statistic, this first part that we've written down is always going to have the t-distribution approximately, okay, because it's always being centred at this true population mean right here. So the t-statistic has one component which is t-distributed from the central limit theorem. And then it has this extra bit that we haven't seen before, right? Now that extra bit isn't there when the null hypothesis is true, so we've spent quite a bit of time thinking about what's going on when the null hypothesis is true, okay, when we were talking about type 1 errors and the significance levels and the critical values and the calculation of p-values. All of that stuff was assuming, was doing those calculations under the presumption that the null hypothesis was true. And when the null hypothesis is true, when mu is equal to m, then mu minus m is equal to 0. So this term here is equal to 0. And this extra term here isn't there. And the t-statistic is approximately normal, and there's nothing else going on, okay, when the null hypothesis is true. But now we want to talk about type 2 errors. Type 2 errors occur when the null hypothesis is false. Okay, so we're no longer in this situation. We now need to think about what happens if mu is not equal to m. Okay, so if this is true, then this additional term is not 0 because mu is different from m. Okay, the standard deviation is not 0, the n is not 0, so all of this stuff is not 0 here. And so the t-statistic is no longer t-distributed. Okay, this is the important thing about the behaviour of this test statistic, is this t-test statistic has a t-distribution, okay, at least approximately, when the null hypothesis is true. But when the null hypothesis is not true, okay, when the alternative is true, then the t-statistic is no longer t-distributed. Instead, it's t-distributed plus this extra bit. Okay, and for our purposes, we'll call that a shift. Okay, that shifts the distribution of the t-statistic away from the t-distribution here, which holds under the null hypothesis. Okay, so in order to start thinking about the probabilities of rejecting the null hypothesis when the alternative is true, then we need to start thinking about this shift. Okay, we know quite a bit now about the t-distribution and how to do calculations with that. But what's going on with this thing, this shift away from the t-distribution that occurs when mu is not equal to m? Well, first of all, we can just look at it and see that it has, we can figure out which way it goes. Okay, so if the mu is bigger than the m, then this top line here is positive. Okay, a standard deviation is always positive, a sample size is always positive. Okay, so if mu is bigger than m, then this entire shift term will be positive, which will have the effect of shifting the t-statistic to the right, okay, upwards, so to the right on the graph. I'll show you some graphs in a minute. Okay, so the shift will be rightwards if the mu is bigger than the m, and of course it will be leftwards, downwards, in a negative direction if the mu is less than m, and that has a negative sign on it. Okay, so that shifts the t-statistic in a negative direction compared to the t-distribution there. All right. Take a look at, so that's the direction. Take a look at what would influence how big that shift might be. Okay, that shift contains a few terms, and it's quite interpretable. So the magnitude of this shift will be large if mu is a long way from m. So if the mu and the m are very different, then that will tend to make this number bigger. Okay, whether that's positive or negative is not really the point here. The magnitude of the shift will be large if mu minus m is large. Similarly, the magnitude of this shift will be large if this sample standard deviation is small. Okay, because it's on the bottom line. So if you divide by a small number, then you end up with a bigger number. Okay, so a small standard deviation gives you a larger shift. And then this square root of n, well, it's kind of on the bottom line twice, notice. So it's in the bottom line of this term here, which is already in the bottom line. So this is like divided by the square root of n, which is just the same as having the square root of n actually on the top line. So if you have larger values for n, you will have larger values for this shift as well. Now the way that these two terms in the denominator are often interpreted is kind of together. because this s divided by the square root of n is what's referred to, and we've talked about this already, as being the standard error of the sample mean. Okay, we mentioned that a couple of lectures back. And so the standard error is estimating the standard deviation of the sample mean x bar as an estimator of population mean. So if the standard error is small, that means that x bar is a precise estimate of the sample mean. Okay, if the standard error is large, then it's not precise. And what this is saying is, if this standard error is small, okay, considered that this whole thing considered jointly, if this standard error is small, then this shift term will be large. Okay, so a precise estimate x bar will result in a large shift here. All right, what does that mean? What's the point of having a large shift? Well, that implies that the distribution of the t-statistic will be shifted a long way from the t-distribution that we're using for the critical values or the p-values, so that a t-test in that case is more likely to reject the null hypothesis. Okay, so the further the t-statistic is away from the underlying t-distribution, we're more likely to get a rejection. Okay, that's kind of the whole point of this, of how we constructed these hypothesis tests in the first place, is the further out into the tails of the distribution, of the t-distribution we get, the more likely we are to reject the null hypothesis. So we just have a term for this probability. So we're going to talk about the probability of rejection now. So the probability of rejecting the null hypothesis when the null hypothesis is actually false, and the word we use for that is the power of the test. Okay, so if the alternative hypothesis is true, then the probability of rejecting the null, which is a good thing, right? That's the correct decision. The probability of rejecting the null hypothesis is called the power of the test against that alternative. Now, one thing to bear in mind about this concept of power is that it's not one number. Okay, when we were talking about the significance level being alpha, and that's controlling the probability of a type 1 error, then that was one number, say 5%. Okay, in the context of power, that's not going to be one number. The power of the test could be different, because we could imagine different values for mu holding under the alternative hypothesis. So power is not going to be one number. It's going to be a whole range of probabilities depending on how close or far away we are from the null hypothesis. And we'll draw some pictures and show you some numbers to get a sense of that. All right, so it's all about analysing this formula right here ultimately. Okay, so if this shift is large, then the t-statistic will be a large distance from the t-distribution, and that will tend to result in a rejection of the null hypothesis, okay, if the shift is large. Whereas if the shift is small, so for example, if the mu and the m are very close to one another, then the shift could be small, and so the t is not that different from a drawing from the t-distribution, and as a result we're less likely to reject the null hypothesis. That's kind of the intuition of this story. Okay? We could put a lot more kind of mathematics behind this, but the intuition is what we need here. So here are some pictures to give a sense of what's going on with this kind of formula here. So here's a picture that we've pretty much seen before, right? So we're testing the null hypothesis that mu is equal to m, and let's suppose that the null hypothesis is true. This is our starting point. Okay, so the null hypothesis is true. This is what's going on in the population. And this picture here, we've seen this kind of thing before. We divide up this region into values of t, if you like, where we reject the null hypothesis. So everywhere above this line here, we reject the null hypothesis. Okay, and everywhere below here, we also reject the null hypothesis. And then in the middle, we do not reject the null hypothesis. All right, so this is a standard 5% test. So the probability of being in this region when the null hypothesis is true is 0.025, and the probability of being in this region is 0.025. So overall, the probability of rejecting the null hypothesis when we add those probabilities together is 0.05. This is the picture we've seen before. Okay, so that's illustrating the probability of a type 1 error, because when the null hypothesis is true, rejecting the null hypothesis would be an error. So 95% we do not reject the null hypothesis. Alright, now what we're going to have is kind of a sequence of pictures here in which we start to introduce a shift. And the exact value of the shift is not so much the issue here, is just to get across the concept of what happens for different magnitudes of shift. So here we're looking at a positive shift, that is, we have the mu being larger than the m under the null hypothesis. And you can see that relative to the null hypothesis case, the distribution of the t statistic here, this solid line, has now shifted rightwards. Okay, the dotted line there gives the t distribution. So the distribution of the t statistic here has now shifted to the right compared to that for the under the null hypothesis. And what that results in is more probability in this solid distribution falling above this upper critical value. So in fact there is now a probability of 0.074 of rejecting the null hypothesis up here, and the probability in this lower tail is reduced down to 0.008. So if you add those two together, we have a probability of 0.082 of rejecting the null hypothesis in this case. And that would be the power of the t-test for this particular magnitude of shift, okay, 0.082. So the probability of rejecting the null hypothesis when the null hypothesis is now false would be 0.082 or 8.2%. Okay, which is not very high, right? So the probability of making a type 2 error here would be all of this remaining kind of probability, okay, being whatever that is, 91.2% I guess is falling in here. So the probability of a type 2 error here is quite high, and that's because the shift is small, right? This t statistic has not shifted very far from the underlying null distribution. So it's very difficult, with such a small shift, it's very difficult to be able to detect that using the t-test. And so the probability of detecting it is small, and therefore the probability of a type 2 error is quite high. Now of course what we can do is increase the value of the shift, and as we do so we will see that the probability, it's a positive shift, so we're going to shift it out this way, so the probability of a rejection out here increases. Now it's up to 0.17, and as we continue you can see the larger shifts, we get more probability in this upper part of the distribution, and we're going to get progressively closer to zero. It never quite gets to zero, but it becomes very, very close to zero in this lower tail as the distribution shifts further and further up here. Okay, and I've actually stopped writing it down there because it's 0.0000 and then something. So there's always some probability here, but it's not worth keeping track of. So now we've got to, the shift has become large enough that the probability of rejecting the null is now above 50%, so 0.516 when the distribution gets out here. Okay, so if we have a shift of this magnitude, such that the centre of this distribution here is now around about 2, okay, so that the shift is approximately 2 in this case, and that's resulted in a probability of rejecting the null correctly of 0.516, and therefore the remaining probability in here of 0.484, isn't it? So that would be the probability of a type 2 error. So what we're seeing is that the larger this shift becomes, the more the probability is of rejecting the null hypothesis, which is good, that's the right decision, and therefore the less probability we have of a type 2 error. The probability of a type 2 error is this remaining probability here under the solid distribution up to the critical value. Okay, and it continues on. I mean, obviously you can continue this as far as you like. This is as far as I went. So the shift here has become larger and larger, and the power of this test when the shift is this big is 0.85. So we're leaving about 15% here for the probability of a type 2 error. Now, none of this, I have to emphasise, is under our control as statisticians. Okay, but this is showing you what are the factors that influence the probabilities of making type 2 errors. Okay? And what we're learning from this kind of picture here is that the probability of making a type 2 error gets smaller as this shift gets bigger. Okay? So if we are testing a null hypothesis where the value under the null hypothesis is very close to the true value of the population mean, then it will be very difficult. That's this kind of situation. It will be very difficult for a T-test to detect that as being an important difference. Okay? But also look at, so we've focused mostly on this, but this standard error on the bottom line matters as well. Right? So if we had, suppose we were in this situation and there wasn't much difference between the mu and the m, then what's in the bottom line is relevant as well. So if we were able to go and, let's say, gather some more observations, increase the sample size, then that would have the effect of increasing the shift. And so increasing the sample size can increase the shift and therefore end up in a situation like one of these ones, where the probability of rejecting the null hypothesis is increasing. Okay, so what this is telling us, what those pictures are telling us, and what this little equation is telling us is having larger sample sizes is good because it gives us t-tests which have increased power against incorrect alternatives. Okay, so just as increased sample sizes are good for the precision of our estimate, x bar, they are also good for the power of our t-test. Alright, we also have here a sequence of pictures here starting from the null case, and just to show you that this all works in reverse. So here's a negative shift. So the only difference in these pictures, this is just for completeness, you'll see the numbers are in fact even the same. What we're seeing here is the same pattern, except now the mu is less than m. Okay, so the shift is in the other direction. So we will have power, the t-test will have power against values of mu which are less than m, and so if the shift gets this far, then we have power of about 50%, 51% here, and therefore probability of a type 2 error in here of 0.484 again. So it's the same kind of story, right? So as we increase the shift, the size of the shift in a negative direction, we increase the probability of rejecting the null hypothesis in the lower tail of the distribution. So all of the same messages work in the same way there. And if we come back to this equation here, all that's different in that sequence of pictures is that the mu now is less than m, so that this is a minus sign for this shift. We can see a little bit of this in this spreadsheet. So this is just where we left off in the first part of the lecture, where we were testing the null hypothesis that mu was equal to m, where mu was set equal to the population value. Okay, so that's, in this case, the null hypothesis is true. All right, let's change that. Let's just put in, let's say, 15 for our value for m. Okay, so that's the null hypothesis is now false. Okay, so the null hypothesis is that mu is equal to m. Mu is 15.92, but m is 15. Okay, and we've got a positive shift, right? So because mu is bigger than m in this case. So if we tested the null hypothesis that mu is equal to m, the correct decision would be reject the null. Okay, then those two numbers are different, so the null hypothesis is false here, and we should reject that null. For this particular sample that we're now looking at, we've got an x bar of 15.3, and when you work it through, we get a t statistic of 0.58 and a p of 0.56, which is not less than 0.05, so we do not reject the null. So in this case, here is a type 2 error. Okay, the null hypothesis is wrong, the null hypothesis is false, but we do not reject it. So that's a type 2 error that we've made right there. Now if we start to replicate this, so I'm just going to command equals and draw another sample here. Okay, and if we draw another sample, we've ended up with an x bar of 15.4, and sure enough we have not rejected the null. So that's another type 2 error. Okay, that's the wrong decision. So let's just go through a few of those. Well, okay, now we've got a different conclusion. So then in the next sample, we've got a rejection. Okay, so the p-value of 0.02 is less than the alpha 0.05. So now we're rejecting the null. That's the correct decision. And what I expect we're going to be seeing, so each time okay, so there's another rejection. So each time we draw another sample, we're getting another decision. In this case, the x bar is up to 16.6, and that's far enough above the null value of 15 that we're rejecting the null hypothesis. So we've rejected, what are we up to now? 3, I think, out of maybe, 6 or 7 that we've drawn. So you can just keep drawing these samples and you can kind of keep count. Okay, so as we're going through here, clearly there's another rejection. So the power of the test in this case is less than, I would say, just based on a very small number of replications there, it looks like the power of the test is less than a half, because it seems like we're rejecting less than half of those drawings. Anyway, so the main point of that little illustration there is to just be clear about what is the correct decision to start with. So the correct decision now is to reject the null hypothesis. So every time we do reject the null hypothesis, that's a correct decision. And every time we do not reject the null hypothesis, that's a type 2 error. Okay? And the power of the test is the probability of getting these correct rejections in this case. Now, if we were to put in, so I've put in a value for m here, which is not really all that far from the true value for mu, right? And as a result, because those numbers are not all that far apart, and we've got a sample size of only 20, so it's quite a small sample that we're dealing with here, a lot of the time the t-statistic is committing a type 2 error, or the t-test is committing a type 2 error, because there's not really a great difference between the population mean and the hypothesized value. So it's kind of hard with only 20 observations for the x bar to be systematically saying that, oh yeah, that's different from 15.92. So, oh, sorry, it's different from 15. Let's be careful here. So the x bar is different from 15. Let's re-specify. Let's go to another null hypothesis now. Let's test the null hypothesis that the mu is equal to 10. Okay. Now 10 is obviously, in this context, a long way from 15. Okay, remember these marks are between 0 and 20 and most of them are clustered up the top end. So 10 is quite some distance away from this mean. So in this case we're tending to get x bar estimates. If you keep track of those, they tend to be around about the mu somewhat. Okay, they're an unbiased estimate of the mu, these x bars. So as we keep drawing samples, we get values that are somewhat around about the mu. And then we go x bar minus m in our t-statistic, and our m is 10. That's quite now a long way away from the x bar values that we're getting. So what we would expect to see is some large t-statistics, which is exactly what we've got here. And so that's a long way into the positive tail now of the t-distribution, once you go in 8.7. And therefore a p-value which is very, very small. So yeah, 4e minus 8 means 0.000, and what is that, 7 zeros before we get to a 4. So that's a tiny p-value, and it's certainly less than 0.05, and therefore we reject the null. So let's just take some repeated samples here. We'll take another sample, and basically the story is exactly the same. Okay, so the x bar is 15.1. That's a long way from 10, and so we get a tiny p-value and we reject the null. And as we repeat this over and over, basically we're rejecting the null. You can see the decision here is not changing. Okay, each sample we get, the x bar is a little bit different, the s is a little bit different, but the overall conclusion that we get from the hypothesis test is that every time we reject this null hypothesis. Okay? So the point of that illustration is to show that here's an example where the shift that we were talking about is going to be very large, because mu minus m in this case is very large. And as a result, in all, close enough to all of these cases it seems, we are rejecting the null hypothesis, so that the probability of making the correct decision is very, very close to 1 here. And the probability of making a type 2 error is very, very close to 0. Okay, so if the null hypothesis is a long way from what's the truth in the population, then the probability of making a type 2 error becomes very small. It becomes easy to tell the difference between the null value and what we're seeing in the data in that case. So it's illustrating that the power of the test, or equivalently the probability of a type 2 error, is not one number. Okay, it depends kind of importantly on whether the null that you're testing is quite close to what's the case in the population, or whether it's quite far away. Okay, so hopefully that helps to give some sense of what those probabilities really mean. Okay, so all of those probabilities that we're talking about in these pictures are referring to the probabilities of what we would see if we were able to take repeated samples from the underlying population and test the hypothesis in each of those samples and keep track of how many of those we reject or do not reject, and then work out the repeated, the relative frequency probability in each of those cases. Alright, so to sum up all of this then, these are some of, I find, the most complicated or conceptually difficult ideas to get your head around when first learning statistics. Because there's a lot of things to keep track of. You know, what are these errors to start with? And when we're talking about hypothesis testing, you need to be careful about whether you are talking about the situation where the null hypothesis is actually true in the population, and then relate that to the decision that you make on the basis of the sample information. So this might take some revisiting and some rereading and perhaps some rewatching of what's in here, just to get your head straight as to what all of these concepts are about. But they are important in terms of properly understanding what's going on with these hypothesis tests. So we've talked quite a bit about the type 1 error, which is the decision to reject the null hypothesis when the null hypothesis is actually true in the population. So that's the definition of the type 1 error. And we attempt to control that when doing hypothesis tests by setting the significance level. Okay, so when we set the either the critical values, or when we set the critical value for the p value to be 0.05, that is setting the probability of a type 1 error. Okay, so the probability of wrongly rejecting the null hypothesis. Okay, so in this hypothesis testing framework that we develop, that probability is set by us, the statisticians. Now, the probability of a type 2 error is just a type 2 error, the definition of a type 2 error is the decision to not reject the null hypothesis when the alternative is true. So obviously that's the wrong decision. Okay? If the alternative is true, then the null hypothesis is false and should be rejected, but is not. Okay? So that's the nature of a type 2 error. Now if you think about the alternative hypothesis, that has a whole range of values within it. Okay? So when we say mu is not equal to m, m is one value, and if mu is not equal to m, then there's kind of a whole range of other values that it could take. So HA being true, in fact, covers a whole range of possible values for mu. The probability of a type 2 error, or 1 minus the probability of a type 2 error, is called the power of the test. And the power will depend on exactly which value of mu under the alternative hypothesis turns out to be true, or happens to be true. We won't know which value it is, but if the mu is a long way away from the value specified under the null, so the distance of the population from the null value, then we'll have a lot of power. So it's quite easy to tell a null hypothesis which is taking a value which is a long way from the population, because the information in the sample will estimate what's in the population. If the null hypothesis is a long way from that, then we'll get a large test statistic, and therefore most likely to get a rejection of the null hypothesis. It doesn't look like what's in the data. And then obviously the reverse is if what's in the null hypothesis is quite similar to what's in the data, then we're much less likely to get a rejection. So it's quite difficult to tell values of mu that are, or values of m rather, that are quite near to mu on the basis of the data. But then the power also depends on the standard error of the estimator, which is determined by the s and the square root of n. And in particular, a large sample size will decrease the standard error and therefore increase the precision of x bar, and as a result increase the power of the test. So the message from all of that is, well, to understand the factors that influence the power of a test, and also just to realise that power is not kind of one number. Power is something which depends on the distance of the null from the alternative, and also the standard error for the estimator. So that's different from this significance level concept, which is a number that we set, 0.05, and we know it. Okay, we would like for our hypothesis test to have high power, but in reality it depends on these aspects of the problem over which we have no control. All right, we'll leave it there.